Welcome to Study Loop.
Here we're given a vector force field that is winds up being 1 over x in the in the horizontal direction, or in the I direction, x direction, 1 over y in the y direction, and 1 over z in the z direction. We can also write this 1 over x1, 1 over x2, 1 over x3, where x1 is x, x2 is y, x3 is z. And if we take the curl of this, we can see that in fact it is 0, and all those relationships are satisfied from the previous problem, and this is in fact a conservative field. We can also just simply see that if we take the I component and take the derivative with respect to j when I is not equal to j, take the derivative with respect to x of j when I is not equal to j. So we take the derivative of this with respect to x2 or x3, we get 0. If we take the derivative of this with respect to x1 or x3, we get 0. And take the derivative of this with respect to x1 or x2, we get 0. So clearly the relationships, we have 0 equals 0 for all of those, all the relationships in problem 79. So then they ask us to figure out what the potential is. Well, we can do that by integrating. And so if we integrate f of x over x, we get that that's the natural log of x plus some function. U would be the natural log of x plus some function of y and z. If we integrate f of y over y, we get that that is natural log of y plus some function of f and x, of x and z. And finally, we get that if we integrate over fz over z, we get the natural log of z plus some function of x and y. And so what we can see here is that if we add all these things up, we'll get a representation of u such that the gradient will equal these, because this function of y and z can be these two things, and this function of x and z can be these two. So to get a complete function, we just have this, and then we can use the properties of the logarithm to show that this is actually the natural log of x times y times z.